At the deepest layers of physics, the distinction between a physical object and a mathematical equation begins to dissolve. The universe appears to follow a singular, uncompromising rule. If the math describing two different systems is identical, then those systems are physically the same. This is the principle of observational equivalence, the logic connecting the classical world to the quantum realm. When we model unobservable classical objects, they follow the exact same equations as quantum particles. Therefore, they are physically equivalent. Our senses may suggest these are different categories of existence, but the math proves they are one and the same. Reality is defined by these shared equations, not by how things appear. We can see this rule in action by looking at the specific physics of being a human observer. To observe anything, you must be anchored to a localized point in space. This embodiment is a physical requirement of the process. This localized perspective creates the feeling that you are a self-contained, independent entity, a singular point in the universe, or a monopole. But this perspective ignores a basic law of thermodynamics. While you maintain a state of low entropy or internal order, the physics of observation requires that you displace an equal amount of disorder elsewhere. The experience of being a self-contained, isolated entity is a physical impossibility. Our localized vantage point is only revealing half of the total system. That missing disorder is actually radiating away from you into the environment you are currently perceiving. You act as an entropic sink, casting disorder outward into your entire light cone the moment you look at the world. The act of observation functions as a thermodynamic circuit. Here, you are one pole, and the external environment is the opposing pole. You are a thermodynamic dipole, discharging entropy to process information, just like a battery discharges charge. Deliberate observation is a physical mechanism, a thermodynamic exchange, that alters the environment by moving entropy. If you were placed in a state of total sensory deprivation, that connection to the environment would be severed. With the connection broken, the observation stops. The circuit goes dark, and you no longer add entropy to the external world. This raises a question. If we are thermodynamic dipoles, why do we only perceive ourselves as singular monopoles? The radiative pole, the entropy we cast into the world, is invisible to us because it is a byproduct of our own perspective. We are the light source that cannot see the shadow it creates. In this universe, there are no true monopoles. Every isolated entity is actually a dipole, with its second, radiating half hidden by the limitations of its own vantage point. This dipole rule doesn't stop at the human mind. It scales up to the macroscopic level of the cosmos, specifically to the black hole. For decades, we have viewed black holes as the ultimate monopoles, isolated voids that consume everything and release nothing. However, a black hole possesses the exact thermodynamic signature of a perfect observer. It is a localized point of absolute informational coherence that absorbs and organizes data from its environment. If every observer is a dipole, black holes must have a radiative pole discharging entropy. Unseen in our universe, the math points to another scalar frame. Here, information consumed by the black hole fuels a white hole in another dimension, completing the cosmic circuit. From the human eye to the supermassive black hole, observers aren't passive witnesses. They're active thermodynamic circuits bridging dimensions, weaving the universe together.